So we can run the model now and explore different configurations which are interesting, and for that we will use, or I recommend using those you obtained from the optimization model. And that is what we have here. The data I showed before contains the initial assignment, okay, to which we added the variability. But prior to that, I'm going to verify that our model is working fine. So what I'm doing here is just using 0 for every single time. So if we have that, and we have one position per item, and if we introduce a capacity which is infinite for all buffers, we have the assumptions that we assumed for the optimization model. I'm going to change the buffer capacity. Instead of 0, I'm going to write infinity. Okay. And okay, although this is not strictly necessary, okay, but I can do it. If I run the model now, okay, it's pretty slow. I'm going to speed it up a little bit. Okay, there you go. Well, you have some results and some preliminary results here. At the very beginning, the model is empty. The system is empty, so you have a weird cycle time, but as time evolves, you have something close to what you would expect. And you have a warm-up, okay, which is 10 hours. So when you get the 10th hour, at the end of it, it resets, the clears all these statistics. So you have new statistics from a model that is already in the steady state. So I'm going to fast forward it, and I'm running the model for 100 days, which is a long time for us to make sure that the results we have here are okay. Again, I recommend watching the descriptive simulation event list, because you should run several replicates and get average times and so on, but this is such a simple case that we might be okay with the information we have. And in this case, what we obtain is what we already obtained from the optimization model. Okay, we have a cycle time of 20, which means an hourly production of 3 parts per hour. What we see here is that the information we get from the simulation model is, let me say, useless when you have no uncertainty, because you knew that beforehand. So you're getting something in a nice manner with this graphical representation that you already knew. So if you leave this variability set to 0, okay, and you change the assignment of tasks to different stations, and you run the model, what you will get is information you already might know beforehand. And that is why the optimization model didn't provide you with solutions different from the one you have, because that was the best if you assumed 0 variability. So simulation is not good to explore different combinations that you actually can explore using an optimization model. That's why optimization is a good approach for combinatorial problems where you have a wide, more than wide, a really, really big or a really, really large set of possible solutions, and you want to explore them in an efficient manner. And when that is the case, using simulation is a very slow process, because it's a manual thing and a costly thing, because you change things, run the model, get results, come here again and change things and so on. So when you can create an optimization model, you rather create it and exploit it. And that is good in itself, and it can be useful for you to explore alternative solutions where you introduce variability. Okay? But what we saw here is that what we get when we share the very same assumptions between or from the optimization model, we transfer them to the simulation model. What we get is what we already knew, which is a good start in terms of the simulation model for us to now change things and see the results when we introduce some real features into our simulation model.